so I haven't updated anything or recorded anything in a while. I've been working on some stuff, and basically been writing my own C++ based mostly header library. I say mostly because there's some limitations in C++ and the way that you can do things while trying to represent registers as pointers. But yeah, so what I have here is a simple Cortex-M4 STM32F429. It has an ESP8266 hooked up over a USART. It has a debug window or a debug output over another USART. It has an I2C EEPROM and has an SD card as well as some LEDs. It is connected to a BB3 benchbox power supply right now to supply. I have my Seger probe up there, and I disconnected my oscilloscope probes because I validated the clocking. I was just going to debug through and kind of demonstrate some of how this is represented and how it works. So I guess without further ado, I'll get started. So I have my Seger RTT stuff wrapped up in some namespacing and stuff, and that makes it easier to deal with. I'm going to skip over some of the stuff. I'm going to go into the clock initialization because it demonstrates a lot of the stuff that I did. So, you know, I've got everything organized by namespaces, and in this case, a lot of these things are inline to reduce the amount of space that they take, such as what I just stepped over, which is disable all IRQs. That should be inlined, and as you can see, it replaced the namespacing and the static inline stuff with literally two instructions, which are basically turn off the interrupts and a not. A lot of this stuff has comments in the IDE. I'm using kdevelop. Most of these registers have word and bit level access, almost all of them. Some things it's easier to do by just setting a value in the word here. So I have a reset value that happens to be in the same area, path, namespacing, whatever, as the RCC. I can go into that a little bit later. But as you can see, if I pull the register information over here, so we're looking at RCC control. So if we go down to the RCC peripheral and we look at the control register, it shouldn't change because the reset value should be relatively what it should be. But the trim values aren't taken into account. So then, as you can see here, I have the high-speed internal on, and this sets it to on, and then it uses a data synchronization barrier to ensure that the clock is turned on prior to going forward, and then there's a do loop to validate that the high-speed internal is ready. I don't have a timeout as of yet. This point here, I'm actually just clearing and ensuring that if I came up from a soft reboot or a software reset, that I reconfigure everything back to the basic startup configuration values, which is very helpful because it puts you in a known state, obviously. So that's where I'm at right now. I'm resetting configurations and ensuring that all of my clock interrupts are disabled. And here's the first spot where I'm using the bit level access, which I'll show a little bit later. Because even though this is a single bit right here, exploiting the fact that true and false are set to 1 and 0 to set these values so that it's more natural. So, you know, as you read this in the microcontroller, on the AHB1 bus where the RCC register set is, or reset and clock control. For the control register, I want to set the high-speed external on bit to true, so I want to turn it on. And here's your high-speed internal, and I've set it on. And then, data synchronization barrier, and then, immediately check to make sure that the high-speed external is ready. And then the same thing for, RCC. I'm going to turn on the bit that turns on the voltage regulator. So that's going to be in the advanced peripheral bus enable one register right here. So we'll turn on the high speed or the voltage regulator output. We'll turn it on, data synchronization, and then inside of the power register now, which should be up here, inside the power register's control register, I'm going to turn on the scaling, the voltage scaling output. And so you'll see that go to mode 1, which it's already at, which is cool, right? So that's default value. So also I'm going to go and set the clock configuration register here to turn on the advanced high-speed bus prescaler. So I'm going to make it so that it doesn't divide, and then, dang it, and then I'm going to do this. I'm going to do something for the prescaler for advanced peripheral bus 2, and I'm going to set that to a specific scalar divider of 2, and then I'm going to set APB1 to divide by 4, which those are the bits for it, as you can see. I mean, they're pretty descriptive. I'm also going to turn on so this is a case here where I can view the configuration in bits for the PLL configuration. I can view them in bits, but it doesn't make any sense to set them in bits, really. And so one of the other things that I've done is, in this case, I've made a function that is present in the location that makes sense for utilizing it with the reset and clock control to take in the information and do what it needs to do. In this case specifically, it wraps up some really ugly conversions where I'm going to do some multiplication, ORing, shifting, left and right to do multiplication and divide, and even in a certain case here, specifically static casting the source bits, which is an enum really, into a uint32 before shifting it to generate the correct value to place in the PLL configuration register. And as you see, it changed, and after that change, I'm going to turn on the PLL. So then, right here you'll see PLL turn on, and then immediately the PLL ready, and then obviously the check, and then I'm going to go and up the settings for the regulator to allow the clock to reach the 180 megahertz that it's currently being configured to. And then, also, I'm going to go ahead and configure flash wait states and stuff like that. And you'll see this in the, you'll see this here. You see every time that I set one of these bits to true or false, it's represented properly in the bit conversion, because 1 is true and 0 is false. And then even the latency here, it's going to work properly. And then, data synchronization value. We can go back to RCC. And now we can take the clock configuration bits and we can change the system clock. So we change the system clock, and then we change the system clock to be the PLL. So we clear it, and then we change it, and you notice that here we are, we've changed it to the value that we want, which is system clock PLL, and then we wait for it, and obviously it's there, and then I'll step into one of these. These are functions that are written within the anonymous namespace, and they use very similar techniques in the framework that I've built, where the it's not SimSys, but it does the same functions, and I believe to myself here that this is way more readable, simply because when you look at the microcontroller data sheet, it shows you where these things are located in the block diagram, and I've basically, with the exception of MCU, represented in here something in the namespace that makes it make logical sense in comparison to the block diagram. So I'm going to turn on the port C GPIO clock, which enables that peripheral clock, and then set the values and stuff, which enables the master clock output 2 in this case. And as you can see, if I go here, not only have I enabled the master clock out, which I'm also going to turn on clock security, and then I'm going to set the vector table location. I'm going to come out, and now my system is running at 180 megahertz, and in my opinion, this is very readable with minimum comments. If I come back to this later, months, maybe years down the line, to update something, this will make way more sense. Advanced high-speed bus prescaler to not be divided, and here we go. I'm going to set the clock configuration bit for the prescaler, and I'm going to set it to no div. Yeah, it's not C, I know, and that's fine, and I don't know right now currently if it actually causes more instructions or not. I'll come down the line on that and look at it later maybe, but it is readable and it seems very good, and it works pretty well. So I get back here 180 megahertz. Well, I mean, this reads in hertz, right? So which you can't tell by looking at the function. It doesn't tell you, not unless you go in the IDE that I use to code. This Ozone debugger doesn't actually display clocks or anything, but I skipped over a bunch of stuff, and as you can see, if I run this, it runs fine. It updates where you are, and the current design pattern after I initialize the RTOS, I start the tasks in a specific order in this case, and then once they've started and had a chance to run and get put on the ready list, I go ahead and I send a system up message, and I send it to the application task, and then that application task sends it out to all the other tasks that'll be needed. That's my current design. I may change that later. It doesn't really matter. And then immediately I go in and set up for and notify the output, the real-time terminal output, that the idle task has started. And then inside the idle task, I check to see if any of the stacks are corrupted, and if they are, it'll print out that the idle task found a corrupted stack, and then it'll send a message to the LED task telling it to stop blinking. And you can see the status light blinking here. This may be not the best design, but right now it's some output that I can see and verify. If I was to restart this debugging and tell it that it corrupted, the LED would stop blinking. I would get a message on the real-time terminal saying that it detected a corrupted stack, and then I'd get this app require, which is something provided by Raging Contracts, would actually tell me exactly where I was at. So in this case, it'll tell me that it's in main CPP at 156 that something happened. So if I didn't know where idle printed this out, not that I wouldn't right now, but if I didn't, it would tell me. And I mean, I could do that. It's not really that hard. I'd go here and go to local data and, corrupted stack, set it to 1, right? And then as soon as I do that, it skips there, prints it out, and then as you notice, the LED stopped blinking. It right now it doesn't turn it off, doesn't turn it on. It just stops it wherever it is. And so, again, like I said, main at 156. So right here, immediately in the source code, I can go to that file on that line and know that this is exactly what happened. And because the LED stopped blinking, obviously in this case, I changed the value of corrupted stack. But as long as the LED task isn't messed up, it'll stop the blinking. I don't, like I said, not the best, but whatever. It works for now to do what I'm trying to do. So I'll get it started again and leave it. And so that's debugging it, and you can see in this window here that the software is running, the firmware is running. And so what I was saying about it telling you all about what's going on, I've got comments in the code that tell you what's going on. So, like for instance, DSB, this is a special kind of barrier. It's the data synchronization barrier. It's got comments, and if I go to the header file, you can see that it's always in line, it's static in line, and it should replace the instruction with this assembly level, and it's got these comments and stuff, right? Same goes for RCC, HSI on. You mouse over this and it tells you what's going on, and whether or not it's read only. One of the things I didn't like about SimSys was that it didn't make sense entirely when you looked at the data sheet and the block diagram. It wasn't organized in a way that matched it, and all the bits were defined in a way that they're defines, and even reading it, it has _I, _IO, _O, and stuff like that, and which you have to dig in to find out which one it is. And I guess it's something that just sits wrong with me, so I changed it on what I'm doing. And so I changed it to read write and read only, and they do the same thing as the IO stuff. And I've given comments and marked which bit they are, so it's very helpful if I find something wrong and I got to go back and I got to compare the bits and the value in the register on the debugger with what it says and what I'm setting, and I got to figure some calculations or something out. It works pretty well, and I've got it in a separate repo as well, so that makes it a bit easier to deal with. I only have the one set of for the 429 right now. But even the header file for my MCU.hpp or my MCU framework or whatever, it tells you, what it includes and where it is and why, And then it gives you the MCU library makeup is as follows, right? So you've got your core with your core peripherals and registers in it, and then you've got your high-speed bus 1, 2, and 3, and then your peripheral bus 1 and peripheral bus 2. And it just seems to make logical sense when you look at it this way. For me at least, it makes it easier to remember where it is in the block diagram. Makes it easier to code, actually. And I can't say enough about how awesome Kdevelop is for this. I just make a regular CMake makefile kind of project, and because I do that, as I'm typing, I can be looking at the block diagram or looking at the data sheet for something I want to do, and I get kind of, okay, yeah, maybe I want to change the flash register, and I want to change that, and I got the bits there, and it doesn't always, for some reason, come up, but usually it does. So one of the things I've done is, I use Z reserved 01 and 02. Supposedly, those things are supposed to come up at the bottom, but whatever. and here's all the bits, right? So, you know, I can enable that interrupt by just saying equals true, because that'll work, you know. So, I don't know. I figured I'd record something and kind of show this off a little bit, as it's really easy to work with now, and maybe I'll forget less of what I'm doing in between sessions when I sit down with my projects that I do on the side. I don't know. Well, anyway, that's it. That's what I got right now. See ya.